Hi, this is Noson Yanofsky. This is analysis of algorithms. We're up to chapter 3, growth of functions. Okay, so today we're going to give the mathematical background that you're going to need for the rest of the semester. Okay, and then already from chapter 4 on, we just do interesting algorithms. So a lot of people find this part a little bit harder, but it's just today, so it's not so bad. We're also going to learn the notation that we're going to use for the rest of the semester. So that's good. Okay, growth of functions is about as follows. Every single algorithm is one of the things to determine how much work the algorithm does, we say, is, oh, how large is the input? So if I ask you to sort something, well, it depends. How long will it take? Well, it depends. If I'm asking you to sort 10 things, then it'll take a short amount of time. If I'm asking you to sort 10,000 things, it'll take a long amount of time. So the question of how long will it take depends on how large is the input. Okay? And the way we say that is as follows. To every algorithm, we're going to associate a function to it. Okay? And the function is from the natural numbers 1, 2, 3, 4. That's the size of the input. Okay, to how much work is done, number of operations. Okay, and what we saw is every algorithm is going to correspond to such a function. The R star means 0 or positive real numbers. Okay. So to every algorithm, we're going to have a function that corresponds, and the function is going to tell us how much work is done. Okay. Question: why R star? There's no such thing as a half of operation or a half of time. Okay, and the answer is, or a quarter or a decimal amount, and the answer is because we're going to use functions like this. Okay, and the output of this functions are not whole numbers. Similarly, we're going to use functions like this, and the output of these functions are not whole numbers. So we give a little leeway by doing that. Okay, so that's helpful. Okay, so this whole class is about comparing algorithms. What's going to happen is we're going to be comparing such functions. We're going to get a lot of functions like this, and we're going to compare them and see how they interact, etc., etc. Okay. Okay. I like to tell a story which has all the ideas of this beginning chapter. The beginning of this chapter. The story is not in the book. It's something I made up. The numbers I made up, but they're not totally crazy numbers. In other words, they're somewhat relevant. Okay? Okay, so when I was growing up, there were Cray supercomputers. Those were the supercomputers of my day. Okay? And these computers, you know, only the NSA and the Army had such supercomputers. Regular people didn't have them. Okay? As opposed to that, my mother bought me a TI 99 4A, okay? And I went under my bed in my mother's house, and I actually found that computer, okay? So this is what I grew up programming on. You put the slides here. I made a lot of Pac-Man and Star Wars using this computer. So that was the computer that I grew up with, as opposed to that. When I was growing up, Cray supercomputers were the computers of the time. Okay, now this computer, and again I'm making up the numbers, did one operation in 1 microsecond, which is 1 over a million seconds. In other words, it could do one operation, it could do 1 million operations in a second. As opposed to that, this was much slower, and it can do one operation in a millisecond, which is equal to 1 over 1,000 seconds. So it can do 1,000 operations in a second. Now, A million is 1,000 thousandths. So this computer is 1,000 times faster than this computer. Okay. Okay, so that's telling you the difference of these things. Now, let's say I had two algorithms, and this algorithm, since I had such a fast computer, I wouldn't care much about the algorithms, and so I would have an algorithm that works f of n is equal to n to the third. Okay? In contrast, when I was programming my beloved computer, I was very much concerned with the algorithms because I wanted my games to work a lot faster, so I was programming these things to work much faster. And so I spent time worrying about algorithms, and sometimes I would, so imagine we can get we're doing an algorithm, solving a problem, and the crazy supercomputer programmer does it in such an algorithm, and I'm doing it, and I can do it in 642n. Okay? So in other words, they're lazy because they have such a fast supercomputer. I was careful, and so I wrote an algorithm like that. Okay. Okay, now we ask the following question. How long will it take to do an input of size 10,000? Okay, legitimate question. Okay, in other words, I have some problem, okay, and the crazy supercomputer can do it on their computer with their algorithm, okay, and my computer with my algorithm, and we want to do the same input, the same input size, okay, which is 10,000. Okay, so what I'd like to do is calculate how long it would take to do it on this computer and how long it would take to do it on this computer with this algorithm. Okay, so let's figure it out. F of 10,000 is equal to 10,000 to the third power, which is equal to 1 times 10 to the 12 operations. That's how many operations are needed to be done if you're going to work it on that algorithm. Okay, good. Now, we're not interested in how many operations. We're interested in how long, time-wise, how long. So we're going to divide operations. We're going to divide the number of operations by 1,000,000, because you can do 1,000,000 operations in a second. And so that gives you 1,000,000 seconds. 10 to the 12 is 1,000,000 times 1,000,000, so this is divided by it, so it's 1,000,000 seconds, which is equal to, divide by 60 to get how many minutes, so you get 16,666 minutes, which is equal to 277.7 hours, okay, which is equal to 11.57 days. Okay, that's great. In contrast, how long will it take this algorithm to do it with my Radio Shack computer? And the answer is G of 10,000 is equal to 6,420,000 operations. Again, we're not interested in how many operations, we're interested in how long, how much time. So we know that it can do 1,000 operations in a second, so we're going to divide by 1,000, we're going to get 6,420 seconds, which is equal to 107 minutes, which is equal to 1.78 hours. Okay? Okay, great. What do we see from this? Okay, well, it's a lot longer to do it here than here. Okay, I try to finish the same job in 1.78 hours than 11.57 days. Okay, Okay, great. I'd like to teach you 4 rules that we get out of this story. 4 different rules that are important. Okay, I'm going to write them in red because we will use them the rest of today, the rest of the semester, and there are 4 rules you should tattoo on yourself and make sure you understand them. Okay, 1, coefficients are not important. Okay, and the way to see that is as follows. Here you have 642. Here you have 1. Okay, and although this coefficient is much larger than this coefficient, still this program, running this algorithm on this computer is much better, faster than running this algorithm on this computer. Okay, and so 642 doesn't add or take away from anything. It's not important, the coefficients. Okay, so that's the first thing, and we're going to see that over and over today, for sure. Okay, second thing, what is important? And the answer is the reason why this algorithm is so bad is because of this n to the third, as opposed to that's an n to the 1. Okay, so leading exponents are important. Okay? Okay, great. Okay, the third rule, so, and we're always going to try to minimize our exponents. And let's just be clear about this. The reason why this algorithm running on this computer is so bad is because this exponent is so large compared to this exponent. Okay. The third thing is a little bit of a technical rule, but we have to do it anyways. Okay. Let me write it in English and then we'll go through some examples. Small inputs are not important. Okay, let's go through that. Okay, you see, for 10,000, this is clearly worse than this. But what happens if I do 10? Okay, so let's do f of 10. Okay, 10 to the third power is 10 times 10 is 100 times 10 is 1,000. Okay, as opposed to that, g of 10 is 6,420, which is a lot more operations than that. Okay, hold on. Oh, I left out 5. Okay, same thing with 5. Okay, f of 5 is a lot less than g of 5. Okay, that means a lot less than g of 5. Okay, for small numbers, this actually works better than this. Okay, and the reason for that is the leading coefficients. But you know something? We don't care about small numbers. Whenever we're evaluating an algorithm, we're not going to talk about algorithms, inputs of size 2, 5, 7, 10. We're going to talk about large inputs. Now, I'm going to be more specific of what I mean by large in a minute. It turns out, if you want to solve just for this particular case, you want to know when f of n is equal to g of n. Let's just solve. We're going to get n to the third is equal to 642n. Divide both sides by n. You get n squared is equal to 642. Okay, and that implies that n is equal to, take square root of both sides, you get 25.3. So the number of operations is equal over here and over here if you have 25.3. Now that still doesn't make it better. It's still better to use this for such a small thing, because 25.3 to the third operations on this computer is a lot better than that. But that just goes to show you where the crossing point is. Okay, and we're going to see this more in a second. You have this function f, you're going to have this function g. G grows smaller than f, okay? But we're not interested in the small numbers. We're only interested in larger numbers, okay? So that's the third rule. Okay, and the fourth rule is a little bit, I'm going to make it as a joke, but there's a very serious point to it, okay? And the idea is as follows: for hardware is not important. Okay? You can spend your whole life trying to get faster computers and faster computers and faster and better this and that, better that, etc., etc. That's not important, right? Algorithms is important. Okay? Algorithms are important. Let's underline that. You see, you can have a computer that works 1,000 times better, faster than that computer, but that doesn't make a difference. The important thing is the algorithm. Okay? The reason why it's better to do it the way you'll finish in 11.57 days here, but 1.78 hours here, is because the algorithm is much better here. I'm sorry, worse here than there. Doesn't matter what the computer is. Okay? And this is a very important thing you have to know. Computers are important, but the algorithm is much more important. And I just want to say a very interesting thing. You work in a company and you say, look, I have a supercomputer. I'll do this as long as it'll take me, I programmed the program. I didn't really think about the program, so it'll take 11.57 days. Okay? As opposed to that, well, anyways, you do that, you get fired. Okay, your boss is going to say, take lunch and don't come back. Okay, but if you say, look, you gave me a lousy computer to work on, but I thought about the algorithm a lot and I did a very good algorithm and I got it down to 1.78 hours, you're getting rehired for sure. Okay, one other thing is my side life. I work in quantum algorithms, quantum computers, and everybody thinks quantum computers are faster than classical computers. What quantum computers are, we're not interested at the moment, but that statement that quantum computers are faster than classical computers is absolutely false. Okay? Nobody knows it, but it's absolutely positively false. The reason why quantum computers are better than classical computers is the algorithms that you use on a quantum computer demand less time than the algorithms demanded by a classical computer. In other words, you can factor a number in polynomial time. We'll explain what that means. You can factor a number within a reasonable amount of time, within a reasonable amount of operations, with a quantum computer, not with a classical computer. Okay? So this is why the whole world is hunting for quantum computers. Okay. So this is very important. One other side historical fact. In our college, the computer department was a breakaway from the math department. In other words, in the 1960s, there were a bunch of math professors, and they decided to make a computer department. Because they were theoreticians, mathematicians, they didn't care about hardware. They cared more about software. Okay? And what this story tells us is they're right. Hardware is not important. Algorithms are important. Okay, let's get into some nitty-gritty. Okay, so the whole thing we're going to do now is, instead of comparing our algorithms, we're going to compare functions. Okay, so I'd like to show you the way we're going to compare. We're going to compare functions in 5 ways, and you'll see it right here. Okay, and the idea is as follows. Take a function g. Okay, that grows a certain way. Okay, and let me just give you the intuition. Okay, n to the third grows a lot. That's what we saw in our thing. As opposed to that, n to the 1, it grows slower. So we're going to write it over here. We're going to write, this is n to the 1, and this is n to the third. Okay, that's the intuition, that the lower you are on the board, the slower you go, the higher, the faster. Okay, and we're going to have 5 different ways of talking about other functions that relate to G. So this is a Venn diagram, and we're going to have these guys. And these are functions that grow like G or slower. And we're going to give them a name. We're going to call this whole set, we're going to call it capital O of G. That's this set. Okay? As opposed to that, we're going to have things that grow the same speed as G or faster. And so we're going to do that like this. And we're going to call this capital omega of G. Omega and O are Greek letters. Okay, now what about things that grow kind of the same as G? That's going to be in here. That's going to be the intersection. That we're going to call theta of G. All these other functions, they grow around the same as G. We're giving you intuition. We're going to go through an exact formalism and an exact proof in a second. Okay, great. But there's 2 more that we have to deal with. This guys, they grow faster than G. They don't grow the same speed as G. Okay? And we call that omega of G. Okay? And these guys down here, they grow really slower than G. They're below G. All these guys are really below G. So we call them little o of G. Okay, so we have 5 different sets of functions. Big O, omega, theta, small omega, small o. Okay, and I'd like to do it, make an analogy. If I give you 2 numbers, x and y, what can you say about x and y? What can you say about x and What can you say about x and y? Okay? If I give you 2 numbers, what can you say about x and y? What's the relationship? Well, there are 5 things you can say. You can say x is less than or equal to y. You could say x is more than or equal to y. You could say x is equal to y. You could say x is less than y. And you could say x is more than y. Okay? Well, guess what? That's exactly those 5 things. 1, 2, 3, 4, 5 is exactly the 5 sets that we have. So I'm going to make that analogy. Again, it's an analogy. We'll do the exact. This is those things that are less than or equal to. This is those things that are greater than or equal to. This is those things that are greater than. This is those things that are less than. And this is those things that are equal to. So again, you have 5 things you could say about 2 numbers. Okay? And you have 5 things you can compare 2 functions and how they correspond. Okay, so that's what we're going to do. Now, keep this picture. It's a nice picture. It's a beautiful picture. It has all 5 of them. But now we have to get into some real definitions of what I mean. Okay? Okay, now I'm going to split the board into 3. Okay, we're going to need more room. It's a small board, but we're going to do it. Okay. And we're going to go through those 3 capital letters first. Okay, so this is going to be, what does it mean to be O of G? That's a capital O. This is going to be, what does it mean to be theta of G? That's a Greek letter also. And this is going to be, what does it mean to be omega of G? These are different things. Okay? You're going to see, okay, I'm sorry. I set up my notes like this. And you'll see that it might be an idea to set up the notes the same way. And we're going to put it in. There's a lot of symmetry here. There's a lot of things that are the same, said different the same way. So keep that in mind. Okay? But we have to be exact because we're making an exact definition. Okay, what's O of G? Let's just use our intuition first. O of G is those functions that grow the same or slower. Let's see if we can say that. This is equal to those f. What type of functions are we discussing? We're discussing functions from the natural numbers to the real numbers star. Okay? Those are the functions that correspond to algorithms. That's what we're interested in. And we say, these are, what's O of G? These are those functions such that for some C member of R plus, what's R plus? Those are positive real numbers. R star could have a 0 in it. R plus is positive real numbers. Okay? And N0 member of N, we'll talk about what that means, what that's about in a second. We have the following. F of N is less than or equal to C times G of N for all N greater than or equal to N0. Okay? Close parentheses. Okay, so it's 4 lines, but it's exact. And you'll see it has all our lessons that we learned. It's O of G is those functions that there's some C, and I'll explain to you what the C is, and there's some N0 such that F, that's what we're comparing, is less than or equal to C times G for all numbers N. And I'll explain to you what it means. Okay? We have a picture for this. It's a very nice picture. It goes like this. We're talking about functions from the natural numbers, so that's here, that's the input size, to number of operations. How many operations we do? Okay, and we have the following. Okay, we're going to have this as F, and this is C times G. Okay. And the idea is as follows. Notice F is below G. That's what we said, it's below it. Okay? And so we say as follows. F grows slower than, or F grows slower or equal to G if there's some constant C, C times G. This is what we said. We don't care about leading coefficients. That was one of the rules that we had. Coefficients don't matter, so we might as well put them in C times G. Okay? And there's some number N0 member of N. This is what we talked about 10 minutes ago when I said we don't care about small numbers. What does it mean we don't care about small numbers? When is a number small? When is a number big? So we're put it in. We say, look, this is N0. I don't care what happens before N0, and we saw in examples, and the small numbers, strange things happen, but after N0, always C times G grows faster than F. Okay? Okay, so what F is bounded, well, what you have these things lower than that. Okay? C times G, and then you have F below it. So that's nice. Okay. Okay. We're going to explain this in another way in a second. Leave me room. You need more room in your paper. I need more room over here, but I'd like to go and do the other one. I want to do this now. It's almost the same. Okay. So G is a function, and this is a set of functions that grows lower than them. A lot of set of functions, like f prime, okay? This function grows a little less than that, and I got to tell you, that function also grows less than G. So all these functions grow less than G, okay? Don't mess up your notes like that. Okay, great. Let's talk about omega of G, those things that grow faster or equal, and you'll see what I mean by or equal. So omega of G, okay, is equal to those functions, and what type of functions are we talking about? N to R star, such that, almost exactly the same, for some C member of R plus and N0 member of N, okay, just like before. Here we have it the other way. C times G of n is less than or equal to f of n. Exactly the opposite. For all n greater than or equal to n0. Okay? So it's exactly the same. The only thing is here, the f's are below the g's. Here, the g's are below the f's. Let's draw a picture of it. Picture is almost exactly the same type of input size. So this is the natural numbers. This is the output, so this is r star. Okay, and what are we going to have? Well, strange things happen in the beginning. Okay. Okay, this is going to be C times G. Okay, but eventually we have an F over there. Again, we don't care about small numbers. So this is an n0. And I don't care what happens before n0, but for all n greater than n0, f grows faster than c times g. Okay? I'm sorry, the board is a little bit small, but we're doing it good. Okay, great. Now, what's theta of g? Theta of g is those things that grow about the same speed as g. So let's do that. Theta of g is equal to, it's going to look a lot like before, but this one's a little bit different. F such that from the natural numbers to r star, just like before. Now we have for C1, comma C2 member of R plus. We have more. Here we had one constant. Here we have another constant. And n0 member of n. Same thing as before. We want to know when we're getting into large inputs. We don't care about small inputs. Okay, and now we have the following. F of n is less than or equal to C1 times G of n, C2 times G of n for all n greater than or equal to n0. Okay? What that means is f grows the same as g. Okay? There might be a coefficient beforehand, there might be a coefficient afterwards, but it's pretty much the same. Okay? And the picture is almost the same. Here's the natural numbers. Here's the real star. Okay? And again, I don't care what happens in the beginning, but this is C1 times G. I don't want to make it particularly loony in the beginning. This is C2 times G. Okay? And basically, we don't care what happens for the small inputs, but at some point, F is between the G's. Okay? But again, we don't care about the coefficients, so we say F grows about the same rate as G. Okay? Okay. Here we say F is bounded above. G is on top of it. Here we say, I'm not going to write it, but you got it. F is bounded below. And here we say F is bounded tightly above and below. Okay? Okay, great. This is a great definition, perfectly understandable. Okay, and this is a formal definition, this is an exact definition. Okay, what I'd like to do now is erase what's inside and give you a whole nother way of looking at these things. Okay, but make sure you understand this. The main idea is, let's just go through the main idea. If G, okay, and we'll go through lots of examples of this when it's done. We have to get it right. If G of n is equal to n to the third, okay? Then this is f's, which are n squared, n to the first, square root of n log n. Those are in here. N to the fourth, n to the fifth, n to the sixth are, and n to the third is in here. N to the third is in here, n to the third is in here. Okay? And in here is only n to the thirds. Okay? But that's an intuition. It gets more interesting. Okay, let's do it another way. Okay? The book does it also this other way. And it's important to see it. People get nervous about this because it uses the concept of limits and calculus, but we're not really using calculus, we're just mentioning it. And again, there's an intuition behind it, so we're going to do the intuition. Okay, great. So here's the intuition. Okay, f is in G of, f is in O of G. Remember, G is a function, O of G is a set of functions. G is a function, O of G is in a set of functions. So f is in this set of function, f grows slower or equal to G, if the following is true. The limit, you don't get nervous now, as n goes to infinity of f of n over g of n, okay, is equal to C member of R star. In other words, if you let's explain what this means. First of all, the limit as n goes to infinity, that's another way of saying I'm not interested in small inputs. I'm not interested in small inputs. Okay? F of n over g of n, if you divide them, you get the coefficient, that coefficient, kind of saying it. Okay? The coefficient could be 0 or any real number. The main point, not infinity. Okay? So f grows equal to, that would be a real number, or slower than, that would be 0. Okay, but it can never go faster. Okay, as opposed to that, let's do this. F is a member of omega of G if the limit, we're always comparing n f to g. Okay, so f of n over g of n. What could it be? Well, this is growing faster, so it's going to be some number, or it could be affinity. So we're going to write it as follows: greater than 0. The limit is greater than 0. Not 0. Okay, here we said not infinity, not 0. Could be infinity. Could be infinity. This one could be infinity. Great. Okay. Great. How about this? What are functions that grow about the same rate as g? Well, f is a member of theta of g if the limit as n goes to infinity of f of n over g of n, okay, is equal to C member of R plus. Not infinity and not 0. They grow kind of the same until a constant, up to a constant. Okay, so here's 3 ways. Notice this is exactly the same, this is exactly the same, this is exactly the same. The question is, what's the output? What's the possible output of our limits? Okay, and again, we're comparing them. Okay, good. Now, there's a special subclass of these guys. Capital O of G, remember the way we drew it, small o of G is a subset of capital O of G. So let's do that. F, okay, so I'm going to draw a little line here, okay, but we're talking about this. F is a member of small o of g, not capital O of g, but small o of g, if the following thing is true. Same thing, limit n goes to infinity of f of n over g of n, we're always comparing f and g, equals 0. What does it mean equals 0? It means when I take the limit, this is very small compared to this. Very small number compared to this. Okay? We also had a subset of this. Okay? A subset of capital omega of g. Capital omega g is those things that grow the same rate or faster. Well, let's see what we mean by faster. F grows like that if, again, we're going to write the same thing, limit as n goes to infinity, we don't care about small inputs, of f of n over g of n is equal to infinity. Okay, it really, f grows faster than g. Okay, and now we have that same thing that we had before. We have that 5 ways of describing these same things using this limits. Let's just remind ourselves, I did it 2 minutes ago, but let's remind ourselves what it means. This is less than or equal to, this is less than, this is equal to, this is greater than or equal to, and this is greater than. Okay, so that sets up these 5 different classes of sets. Okay, great. Okay, I'd like to put this all into another picture. Again, the book is a little bit low on the pictures, so I like pictures, and we'll do it. But you'll see it works out very nice. Okay, anyways, pause the computer if you pause the computer and copy it. Okay, and the idea is as follows. I need a black pen. And the idea is as follows. Here's 0, here's all the real numbers, here's infinity. Okay? And we have lots of different ways of breaking this up. Okay. If you look at the limit, this is O of G. If you look at the limit and you get out anywhere till that, this is omega of G. If you look at the limit and you get not 0, but not infinity, that's theta of G. Okay, great. 2 more. If you look at the limit and you get 0, that's going to be O of G, small o of G. Okay? And if you look at the limit and you get infinity, that's small omega of G. Okay? And again, I'm going to do the same idea again. This is less than or equal to, this is less than, this is greater than, this is greater than or equal to, this is equal to. Keep those symbols in mind. Okay, great. Okay, that's enough theory, but let's work out some nice examples. Let's work out some nice examples. Okay, so that's enough theory. Now let's get into real life examples. Okay? And the idea is as follows. Let's just go through this. Take the function 3, 5, 8, 7, n to the third. Okay? I want to know how that compares to n to the third. Okay? And if we do it, we do the limit as n goes to infinity of 3, 5, 8, 7, n to the third divided by n to the third. What do we get out? Well, this cancels out with this, and you get out 3, 5, 8, 7. Now, that's a particularly simple case. The point is, that's a real number, therefore this is true. What's also true, and again, you have to rewrite this. I have an eraser. What's also true is this is true, and this is true. So it grows, all three of them it's true. What's not true, this, instead of saying it not true, I'm going to cross it out. This is not true. 3, 5, 8, 7, n to the third does not grow slower than n to the third, because otherwise this would be a 0. What's also false, what's not, it doesn't belong, is 3, 5, 8, 7, n to the third does not grow faster than n to the third. Okay? Because this is not infinity. Okay? So it fits in there. Okay. But let's do something more. How about, and again, you have to rewrite, I don't. How about n to the squared? Well, if we put the square here, okay, and then this n to the third, so this is going to cross out with this. This is going to go to this is going to be n, okay, and then you have the limit of this goes to infinity actually, and so what we could say is this grows faster than that. So let's see what that means. That means this is true. It grows faster than n squared, and also, more importantly, this is true. It grows faster than n to the third. Okay, great. What happens if I put a 4 over here? Okay, then this becomes n to the third divided by n to the fourth. This cancels out with a lot of them, but leave one n. This goes to 0, and so what you're left with, this is a member, this grows slower than this. Okay, this is also true. Okay, so you get all these different things. Okay, a few, the main idea is as follows. If you have a function f of n equals minus 16 n to the third plus 45 n to the fourth minus 28 n to the second plus 16,326, okay, such a function, what you do is you look at the highest exponent, you ignore the coefficient, and you just say f of n is a member of theta of n to the fourth. It grows about the same size as n to the fourth. That's the main determinant of what you're dealing with. Okay, great. Okay, I'll just work on just the classes. Theta of G, that's those things that grow the same, is equal to O of G intersect omega of G. Okay, this was clear when we drew that picture in the beginning. Okay, this is O of G, this is omega of G, the intersection is theta of G. Okay. Okay, so the intersection is those things that are in both. If it grows the same speed, that means it grows the same speed or slower, and the same speed or higher. Okay. Okay. Here's another one. F of G. Stupid. F of n is a member of O of G of n. Okay, let's leave out the of n. This makes more sense. Okay? If this is true, if and only if, that means the other way is true, is G is a member of if F grows slower than G, then G grows faster than F. Okay? Now, just remember this stands for less than or equal to, this stands for greater than or equal to. Because of this, if I want, I can write a book and never use this. Because every time I wanted to express something like this, I would just flip it around and do this. Just like I can write an entire math book and never use this symbol. Because every time I want to write x is greater than or equal to y, and I don't have that symbol, all I have to do is write y is less than or equal to x. Okay? So a lot of books do not use this symbol. And in fact, our book also, it mentions it, but it doesn't really use this symbol. It uses this mostly. Okay? And again, whenever you want to write it, you can write one or the other. Okay? One more relationship amongst the classes of functions. If you have f is a member of O of G, and G is a member of O of H, then, okay, F is a member of O of H. Okay? That says if F grows the same or slower than G, and G grows the same or slower than H, then F grows the same or slower than H. Okay, so that works out very nicely. It's just like this. If x is less than or equal to y, and y is less than or equal to z, then x is less than or equal to z. And that's something you know since 6th grade. Okay, great. Okay, I want to talk about all these different classes kind of in order. Okay, so we have functions that run n. Okay, we have a lot of functions that run n squared. Okay, we have functions that run n to the third. Okay, and then what we saw, there are things like this. In here, there's n log n. That's going to be a popular one. Okay, so it's not n, it's not, okay, what else is in there? N times square root of n. N times square root of n is n to the 3 over 2. Okay, that's n to the 4 over 2 if you want. Okay, and this goes on until you have, I don't know, you have n to the 4th, you have n to the 5th. Amazingly, in our book on algorithms, there are very few algorithms above n to the 5th. I don't know why. What does that say about human beings? Why can't we think of more advanced algorithms? But I don't want to really talk about it. Okay, and then you get to the n to the 100. Okay, but you can go on. Okay, and when you go on, you get 2 to the n. But there's something before 2 to the n. Once you have, for example, 1.1 to the n is this is exponential, but this is also exponential. Now, I once told this in a class. I said, you know, n to the 100, and then you have 1.1 to the n. And the guy, it was a kid in my class, whatever, and he said he doesn't believe it. He says, you plug in 10 here, 10 to the 100th power is a Google. 1.1 to the 10th power is nothing. Anyways, but I explained to him we don't care about small inputs, and he didn't believe me. And so I made him write a program, and he wrote a program, and he found the point where this grows faster than this. Something like 9,260. If you plug in n for 9,260 into here and here, you'll see that this number is greater than this number. Now the numbers are, 65 digits at least, or 100 digits at least. No, probably more. Anyways, 300 digits or more, but the n for which these cross over, this is bigger. So again, all these things are bigger. And of course you can always go on. You talk about 3 to the n. You can also talk about n factorial, or even more than n factorial is n to the n. And of course you can talk about n to the n to the n. You can always find worse and worse algorithms. Algorithms that take more and more time. Hard to find problems that have such solutions, but they exist. As opposed to that, you could talk about square root of n over here. You could talk about the 100th root of n over here. Okay? But all the way on this side, and I'm sorry I ran out of room, you also have ln of n. Log of n. Okay? But there are things smaller than log of n. For example, log of n. Okay? Let me just show you how absolutely small this is. Okay? Log of 64,000, maybe it's 65,000. Hold on. $65,536. Okay, that's equal to log of, that's 2 to the 16th. What's 2 to the 16th? And that's 2 to the 16th. So this becomes, the 16 comes over, well, I'm sorry, I forgot the other log. Okay, the 16 comes over here, and so this becomes, this is equal to 4. Okay, so you could have an input of size 65,000, and it's only going to do 4 operations. Okay, that grows very, very, very slow. Okay, but it's interesting. It's useful. How slow does it go? It grows just as slow as this grows fast. Okay. In other words, plug in 4 here. 2 to the 4 is 16. 2 to the 16 is 65,000. So it's the same thing. So they're kind of like mirror images of each other. So exponential is here, logarithms here. The difference between this side, which can go on forever and ever, you can always get more complicated things, is this does have a left side, this does have a wall where it stops. And such things are cool, we write like this, O of 1. What does O of 1 mean? Well, it's not really one operation, because you could have a leading exponent, you can have a coefficient there, like 642 times 1. But these, which we call constant functions, these are functions where it doesn't matter what the size of the input, it's going to do a constant amount of operations. Whether or not you're trying to do an input of size 63,000 or a size 28,000 or whatever in between, okay, it's always going to do a constant amount of operations. Okay, obviously such algorithms are not very interesting, but we're gonna talk about them. So again, this side can go on forever and ever. This does a boundary. You can't get better than that. Constant amount of operations. That's absolutely, that's the bare minimum. Okay, great. We have 3 rules about this spectrum, and it's not really a spectrum because there are certain things that are uncomparable, but we don't want to get into the weird stuff. But there are 3 interesting rules here, of which I said. So if you have x is less than y, okay, so this is the first rule. If x is less than y, then n to the x, n to the x is going to be a member of O of n to the y. If x is less than y, then, okay, these are real numbers, then n to the x grows slower than n to the y. So that's one important thing. Okay, 2, for all x, okay, log of x, log of n grows smaller than n to the x. In other words, as far as you go, this can be 100th root, that's 1 over n, okay? But this guy is always smaller. Logarithms always grow smaller than any, these are polynomials, okay? So polynomials, larger polynomials sit inside smaller polynomials sit inside larger polynomials, and logarithms sit inside all polynomials, any polynomial whatsoever. So even if x is 1 over 100, still this grows smaller. And the third rule is the opposite. For all x, n to the x grows smaller than 2 to the n. Okay, so those are exponential functions, and as big as a polynomial is, it's always going to be smaller than exponential. I don't even need the 2, I can do 1.1 or 1.000000001, okay, to the nth power, and this will be true. Okay, great. So you have that. Let's do some English. These algorithms show up all the time, and so they have special names to them. Okay, and so we mentioned some of the names, but let's do them anyways. Functions that grow constant, these are called constant algorithms. Algorithms that run in this time are called constant algorithms. Algorithms that run in this time are called logarithmic algorithms. Okay. Algorithms that run like this are called linear. Okay. Many algorithms that we're going to deal with, we're going to aim for this, n log n. Log, and we're going to spend some time talking about log in a minute, but logarithm is all about splitting things. How you can split things, how much you can split things. Splitting things is all about recursion. Okay, so we have a big problem, we split it up. So we're going to see this a lot. It doesn't have a special name, but it's called n log n. Okay, O of n squared are called quadratic algorithms. Okay. O of n to the third are called cubic algorithms. Okay. O of n to the c is any number, are called polynomial. Okay. O of c to the n, where c is greater than 1, is called exponential. Okay. And O of n these are called factorial algorithms. Okay, so lots of different names for lots of different algorithms. Okay, great. Okay. I've taught this class a lot, and I know the math that's needed for this class. Okay, I know what we're going to use and what we're not going to use, and I know what students need reminders of. And so the rest of this video is going to be just some math things that we have to know and we have to appreciate beforehand. Okay, so on page 56 or 57 is a review of logarithms. Okay, and it pays to spend some time doing it. I know you all seen logarithms, but we could see it again. Never hurts to see logarithms again. Okay, so I like to think of logarithms as the game Jeopardy, where they give you the answer and they're asking you what the question is. It's kind of a similar type of thing. Okay, the hard part in life is to get a good marker. Okay, what this means is Well, the way to think of this is if it'll live, a to the y is equal to x. Yeah. I'm going to take a 1 minute break and find a good marker. Okay, so we're back to logarithms, and logarithms are basically exponentials. Okay, if you know exponentials, then you know this. I like to think of it as Jeopardy. Log base a of x is equal to y. That means a of y is equal to x. Another way of saying it is, if I give you the answer x, what do you have to raise a to in order to get x? Answer, a to the y is equal to x. So it's like Jeopardy. If you're given the answer x, what's the question? And so you have that. Okay, well, let's just do a quick example. Log base 2 of 1024 is equal to 10. What do you have to raise 2 to in order to get 1024? Answer, 10. This is another way of saying 2 to the 10 is equal to 1024. Okay? So you already have seen it. Okay? Okay. And in fact, logarithms and exponentials are opposite operations. Let me explain to you what that means. Take a number, add 5 to it. Whatever number it is, take a number, add 5 to it. Okay? Now take that number and subtract 5. You're going to get back the original number. Okay? And what that means is addition and subtraction are opposite operations. So too, exponentials and logarithms are opposite operations. Okay? And you get that if the answer gives you the question gives you the answer, that means that they're opposite operations. So let's do it. Okay? Take a number x. Take log base b of it, log base a of it. Okay? Okay, great. Now take the exponent of that. Okay? Now ask yourself the following question. What do you have to, close that off. What do you have to raise a to in order to get x? Okay? Whatever that number is, raise a to it. Well, what are you going to get? Let's say that again. What do you have to raise a to in order to get x? Some number. Okay? Well, take that number and put it as an exponent to a. Okay? Well, what do you get out? Answer, x. Okay? So this says if you take a number and then you do logarithms and then you do exponentials of it, okay, you get back the original number. Okay? That's a way of talking about exponentials. So it's given the opposite things. Okay? Let's do the other way. Take a number, take a to raise to that number, then take the logarithm base a on this. Okay? And now ask yourself the following question. What do you have to raise a to in order to get a to the x? It's like a self-fulfilling prophecy. Okay? And the answer is x. A to the x is equal to a to the x. Okay? These two equations show that logarithms is the opposite of exponentials. Okay, great. Now, we're going to go through a lot of different properties of logarithms, but beforehand we have to do some lingo. Okay? This is all from page 56 and 58 of the book. Okay? Again, I cherry pick what we're doing because I know what we're going to do. So, I know what we're going to do in the course. So I don't do everything, but I cherry pick some things. Okay, so log just Lg of n is equal to just getting the notation right. Lg of 2 of n. This shows up so much in computer science because we're always splitting things into 2, or we're dealing with 2 letters, or 0 and 1, or something like that. This shows up so often that we shorten it from log to Lg. Okay? There's also ln of n, which is logarithms base e of n. We're barely ever going to use this. Okay? This is something for calculus, for engineering and stuff like that. We don't use it. Lg to the k of n is equal to Lg of n to the kth power. This sometimes we get to use. And again, we talked about this, Lg of n, okay? And that's equal to the log base 2 of the log base 2 of n. Whoops. Okay? And we just mentioned this goes much slower than everything else. Okay, now that we have the lingo, I'd like to go through a few properties of logarithms. Okay, I'd like to go through a few properties of logarithms and prove them by looking at exponentials. We know everything about exponentials. We've been doing exponentials since 4th grade. Okay, logarithms is just the same thing as exponentials, so we're going to do the same thing. So first of all, if x1 is greater than x2, that implies log base b of x1 is greater than log base b of x2. Okay, this is called a monotone function. If one number is bigger than the other, then the logarithms of them are bigger. This is the same thing as follows. If y1, okay, now I'm going to do the exponential property. If y1 is greater than y2, that means b to the y1, this implies b to the y1 is greater than b to the y2. Okay, so this property we know since 4th grade. This property is saying the same thing, but if you have to stand on your head. Okay, log base b of 1. What do you have to raise b to in order to get 1? Answer 0. Well, it's the same thing as b to the 0 is equal to 1. That you know since 4th grade. Okay, log base b of a to the b. What do you have to raise b to in order to get a to the b? And the answer is a. We just did that 2 minutes ago as inverted things. Okay, and that basically says b to the a is equal to b to the a. Again, that's by definition. Okay, now for an important property which shows up very often, log base b of a times c is equal to log base b of a plus log base b of c. Okay, and this corresponds to b of y1 plus y2 equals b of y1 times b of y2. Okay. Again, if you add exponents, you get a multiplication of this thing. This means y1 plus y2 copies of b. Well, you can separate it like this. Notice what's going on here, and we're going to do this again and again. Logarithm made a multiplication into additions. Exponentials takes an addition and makes it into a multiplication. Very important. Okay, now we have to take a 1-minute historical background. Why did they invent logarithms? Okay, why did they even invent logarithms? This is not in the book, but it's just something that you should know. Okay, and the answer is as follows. Okay, logarithms were invented in like the 1600s, and they were invented exactly for this reason. Okay, but it's a very algorithms reason. Again, even though it was invented in the 1500s, it's the reason why they're doing it is an algorithm. The idea is as follows. Let's say I wanted to multiply two n-digit numbers. Okay, let's say I wanted to add two n-digit numbers. So I have x1, x2, x3, xn, and I want to add y1 plus y2 plus y3. I'm sorry, these are digits, yn. I'm adding these digits. How do you add numbers? Okay, well, this plus this, and you put down this, and sometimes you have a carry, and sometimes you don't. Okay, so this will be zn, z3, z2, z1. Again, each time, sometimes you have a carry, sometimes you don't. Conclusion. How many operations do you have to do? How many operations do you have to do to add numbers? point is, this plus operation is an n area operation. You have to do n small operations. Okay? So addition is O of n. It's a linear algorithm. Okay? As opposed to that, multiplication, how do you multiply two n-digit numbers? It's much more complicated. You have to multiply this digit against every one of those. You have to multiply this digit against every one of those. You have to multiply this digit against it. So you have to multiply every one of the bottom digits times every one of the top digits. Okay? And then you have to add them all together. So that's a lot of work. So it turns out that multiplication is O of n squared. Now we know the difference between O of n and O of n squared. That takes a lot more time than that. Okay, great. By the way, great. Okay, here's why logarithms were created. Because they made books which have logarithms. They fix a base, okay, and they made giant books called logarithm books that you can look up, plug in a number, and it's going to give you a logarithm to that base. Okay? This is in the 1500s and the 1600s. They had such books. Okay, now, here's what you do. Let's say you wanted to multiply two large numbers, and I mean, let's say 20-digit numbers, okay, with decimal points, etc. So one way is multiply the two numbers. That's it. I get A times C, finished. Okay, but that's an n squared operation. Here's something else you can do. You can look up in your book log base b of a. Okay. In other words, search. So watch it. So one way of multiplying two numbers is an n squared operation. Let's do another one. One, search for log b. So that's one search. Search in your book. You have a book. It's ordered by A. Okay, and like a telephone book, it's ordered by your last name. So this is going to be ordered like that. Okay, search for that. So you need another search. So that's two searches. Then do one addition. Okay, and then you have this number plus this number. Fine, but you don't want this number. Oh, this number plus this number gives you this number. That's fine. Okay, but you don't want this number. You want A times C. So what you can do is reverse search. In other words, look at the outputs and see what the number is. So one, reverse search. Okay, it turns out searching is not such a hard operation. We're going to see later on. Searching an ordered list is not such a hard operation. So these three searches plus one addition is much better than an n squared. This is exactly the reason why logarithms were created. They were created to help you multiply numbers quicker. Okay? The main point, the shocking point is this was done in the 1700s. Okay? I think. Could be wrong about this. This was done very early, long before there were computers doing this. Okay? And the reason why they did it is purely for algorithm reasons. Okay, great. Okay, so these are different properties that we have for about logarithms. Let me do a few more. Okay. We can extend that. Let's do it this way. Log base, what did I have before? Log base b of a plus a is going to be log base b of a plus, times log base b of a. Okay. Another way of saying that is this is log base b of a squared is going to equal to, notice two of these, so this becomes 2 of log base b of a. Okay, so notice what happens here. The exponentials become multiplications. Okay? This is, the exponentials become multiplications. Now, I don't have to just multiply 2. I can also generalize that. Not only 2, but a to the n is equal to n to log base b of a. If I take n copies of a times a times a times a times a, okay, I'm going to get n copies that I'm going to add together, and I get this n. And so again, this n goes forward. So exponentials become multiplication. Okay, and this is not strange because we know this from exponentials. B of a times n is equal to b of a to the nth power. Multiplying by n, okay, so let's do this. Logarithms takes exponentials and makes them into things that you multiply with. Exponentials take things that you multiply with and make them into exponentials. Okay, so this all works out. Okay, great. Let's do 2 more properties of logarithms, again, that we're going to use all the time. Okay, theorem. I'm going to prove it in a second, but let's first state it. Log base b of a is equal to log, let's leave the parentheses out, log base c of a divided by log base c of b. Okay, and the idea is as follows. Your calculator only has log of probably base 10. We're mostly interested in log base 2. So how do you write a logarithm of b in terms of other logarithms? Okay, we'll see this in a second. Let's first give this as, how do you do this in terms of exponentials? It goes as follows. B of a is the same thing as, here I'm using base b, here I'm using base b. So b of a is the same thing as, I can do this in terms of c, base c. This is in terms of base c. Let's do it. Ready? Base c of log base c of b. What do you, forget about that. What do you have to raise c to in order to get b? Raise c to that. That gives you b. Okay? Now you have the a. So another way of writing b is c raised to log b of c of b. Okay? This again is that inverse formula. Let's close it up. Let's just focus in on what's inside the parentheses. C raised to the log base c of b is another way of saying b. Okay, great. Now, I just want to think about what this does. What did we just see about exponentials? This is another way of writing this. We can write this another way. Okay? This is c raised to the a times log base c of b. Okay? Okay, notice what I just did here. I said, oh, you want to know what b raised to the a is? That's the same thing as c raised to the a, but I need some extra term to fix it. Okay? So this is the intuition, okay, behind, this is the intuition behind this theorem. I'd like to prove it anyways. This actually proves it, but I'd like to prove it a nice way, a very interesting way of proving it. Okay, so let's prove it. Okay, you don't have to know this. You just have to understand the following. I'm using base b here. I want to use base c. I'm showing you how I can use base c here also. Okay, and when I want to do exponentials with base b, I can also do the same exponentials with base c. Okay, let's prove this. Why is this true? And the answer is, let's do it. Okay. Look, I want to know what log base b of a is. I don't know what it is, so proof. Okay? when I don't know what something is, I set it equal to a variable. That's a typical mathematical trick. Okay? If you don't know something, give it a name. Okay? Very good. Now, I still don't know what y is, but I know what this means. What does this mean? It means b to the y is equal to a. That's the definition of logarithms. B to the y is equal to a. Okay, so I don't know what y is, but we know this is true. Now I do have a function called log base c. So I'm going to take log base c of both sides of this. Again, I don't know what this is, but this means the same thing as this. So log base c of b to the y equals, if I take log of this, I got to take log of this, log, whatever operation I do on one side, I got to do it on the other side. I get that. Now, I still don't know what y is, but one thing I can tell you is I can bring that across. So I get y times log base c of b equals log base c of a. Divide both sides. I want to solve for y. That's the purpose. I'm trying to find out what y is. So I divide both sides by y, by log base c of b, and I get log base c of b. Okay, and I get y is equal to log base c of a divided by log base c of b. Okay, which is exactly what we started with. So again, what's log base b of a? Well, it's equal to y, which is equal to this. Okay, so the main point of this theorem is that I can write logs of base b in terms of log of base c. Let's just write that out very, very carefully, what that means. If I was, there I am. Okay, that's a theorem. Let's just use an example, what that means in terms of real life, in terms of your real, calculator. It says, let's say I want to know log base 59 of x. I don't have a calculator that does log of base 59. Let's say you have a calculator that does log base 78. Again, I'm using two crazy numbers. Again, your calculator probably, and you need a calculator for this, your calculator probably has log base 10 and probably log base e, because that's used a lot by engineers. Okay, so this becomes log base 78 of x divided by log base 78 of 59. The main thing to notice here is that's a number. That's just a regular number. You'll use another word, a coefficient. That's just a coefficient. Let's write this out another way. This is just 1 over log base 78 of 59 times log base 78 of x. So this function is a coefficient times this function. Another way to say that in terms of us algorithms people, is log base 59 of x is a member of theta, that's a coefficient of log base 78 of x. They grow at the same rate, up to a coefficient. They grow at the same rate. Obviously, this grows faster than this, whatever, it doesn't matter, but up to a coefficient, they're the same rate. Okay, so this shows you how to use it. One more idea from logarithms. This idea we have to use exactly once in the entire course. It's actually the only time I've ever seen it used, period, but it is a fact, and we'll do it. Okay, so it goes as follows. Theorem. We'll prove it in a second. It takes a second to prove it. A to the log base b of c is the same thing as c to the log base b of a. Okay? Notice what's going on here. The a and the c are swapping. Okay? In terms of exponentials, this is like this. B of a to the c is equal to b of c to the a. Kind of similar to that. Okay? What's the inner exponential? What's the not? Anyways, let's prove it. Proof. Simplest proof in the world. Okay? A of log base b of c. Question. Is this equal to this? That's the question. C of log base b to the a. Are these two equal? Answer, I don't know. But let's take logarithms base b of both sides. Okay, we'll see what happens. Again, I'm not sure if they're equal. I want to prove that they're equal. I'm not sure if they're equal. So, but I'm going to do one operation to these two numbers. I'm going to do the same operation to this and to this. I get log base b of a, and here, question mark, log base b of this. Okay, great. Now, we know that exponentials become multiplication. So let's see what this becomes. This becomes log base b of c times log base b of a. Question, is that equal to log base b of a, that's this guy, comes to the front, log base b of c. This is log base b of c times a, log base b of a times c. X times y is equal to y times x. You learned that in first grade. Okay, so these two numbers are equal. Okay, so look, notice what we have here. We took a logarithm of both sides, and we got the same number. Okay, how could you do a function that's monotonic, that takes different values to different values, and it should end up to the same value? Answer, it must be that they started off the same value. Okay, logarithms takes different numbers to different numbers. It's a one-to-one function. Logarithms take different numbers to different functions. They take the same number to the same functions. So two things end up in the same number, they must be the same thing. Okay, so that takes care of that. Okay, some more math, which again, it's in the appendix, but it's something we have to see. So this is in page 1147. I told you this part of chapter 3 we use as a way of we use as a reminder of some of the math that we're going to need. Okay, so let's do some math. Okay. Some things we saw, just remind you, a1 plus a2 plus a3 plus da, 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 da. We saw this in discrete structures. We write this as sum of I equal 1 to k of ai. Okay? And if we want to talk about multiplication, we have the same we have another symbol. We do capital pi. This is capital sigma. I told you Greek is a prerequisite for this class. Sigma for sum, pi for product. Multiplication is product. Okay, so this is ai. Okay, and just two or three good rules that we're going to use for this, but one rule we already saw. The sum of I equal 1 to n of I is equal to n times n plus 1 divided by 2. So that was a nice rule we saw that uses this. Okay? We need another rule, and that's called the geometric series. I think they teach it in pre-calculus around here, but just in case we have to do it again. Okay, and let's prove this theorem. Now let's first state a theorem, and then we'll prove it. The sum of I equals 0 to n of x to the I is equal to, okay, so this is a theorem. Okay, it's equal to x to the n plus 1 minus 1 divided by x minus 1. Okay. I want to prove this theorem. Okay. So, but before I prove it, notice we did things like this before. Notice, instead of adding up things, what I could do is take an exponential, subtract, divide, subtract, a few operations rather than a loop of operations. So this is a time-saving thing. Also in terms of algorithms, besides the fact that it's going to help us a lot. Okay, let's do the proof. Proof. Okay. Y, I don't know what this is equal to, but I'm going to set it equal to y. The sum of I equals 0 to n of x to the I. Okay. Okay. I'd like to solve for y. Okay. I don't know how to do it, but I have a name for it, and now I can do something else. I can multiply it by that. Okay. I can multiply x times y. Again, I don't know what y is, but I can multiply. What that does is it multiplies each one of these. So this becomes, you ready? The sum of I equal 1, because x to the 0 times x to the 0 times x is going to be x to the 1, x to the I till n plus 1. The last term is going to be x to the n times y is going to be x to the n. Okay, great. I don't know what this is equal to. I set it equal to y. I still don't know what it's equal to, but I multiplied it by x. Now what am I going to do? I'm going to do the following. xy minus x. No, x minus x minus y. Okay? Okay. This is equal to, let's see what it is. Look, I have all the terms from 1 till n plus 1. Okay, and I'm subtracting the terms from 0 to n. So we can write it as follows. I have x to the n plus 1 plus x to the n plus x to the n minus 1. I don't know why I did it backwards. Plus, plus, this is x to the 1. Subtract. Okay, subtract this. So this is, I don't know why I did it backwards, minus x to the n plus x to the n minus 1 plus plus x to the 1 plus x to the 0. By the way, what's x to the 0? That's 1. Okay, I'm subtracting this. This cancels out with this, this cancels out with this, this cancels out with this cancels out with this. I'm left with x to the n plus 1 minus x to the 0, which is 1. Okay. Okay, so look what I got. I have x times y minus y is equal to x to the n plus 1 minus 1. Divide out by y, and so I get y times x minus 1 is equal to x to the n plus 1 minus 1. Now, my goal in life is to solve for y. I don't know what y is equal to. So I divide this by x minus 1. I divide this by x minus 1. Okay, and I get y is equal to x minus 1 divided by, x to the n plus 1 minus 1 divided by x minus 1, which is exactly what we have. Okay? Great. So this is a theorem. That's a nice proof. You can pause and write it up. It's an important proof. Okay, let me show you two instances of where you're going to do this. Two very nice instances of where this is going to work. One you saw the first day you walked into programming class. The sum of I equals 0 to n of 2 to the I. If you have n bits, okay, and each one of them can be 0 or 1, and you want to know how many numbers you can represent all together, well, that tells you 2 to the n plus 1 minus 1 divided by x minus 1. 2 minus 1 is 1. So that takes care of that. So this is something you've seen since your first day. Let's do another one. Okay. The sum of I equal 1. I'm sorry, let's do 0. 0 to n of a half to to the ith power. Okay. This is going to equal to, just plug it into the equation, x is equal to a half, so this is a half to the n plus 1 minus 1 divided by a half minus 1 is minus a half. Okay. Okay. So that's an interesting thing, but I'd like to do it a little bit more interesting. Okay. The sum of I equals 0 to infinity. We don't usually deal with infinity. To the I is equal to a half to infinity plus 1. I don't care what infinity plus 1 is. The point is, a half to infinity is 0. Minus 1 divided by minus a half. Okay. Okay. What's minus 1 divided by a? That's 0. This goes down to 0. This becomes 2. Okay. Let me just show you what this is geometrically. Okay. Start off, I is equal to 0. What's a half to the 0th power? That's 1. Take a 1 by 1 square. Now do add a half of that. So that's a half. Now add a quarter, because that's 1 to the half to the 2 is a quarter. An eighth, a 16th, a 32th, a 64th, a 1/28th. Eventually, what are you going to get? You're going to get 2 by 1 square. Okay, so this is an infinite process. That's something. This has something to do with something called Zeno's paradox. You can see that another time. Okay, one more page about trees, binary trees. Okay, and we're going to spend a lot of times with binary trees. Let's just remember what a binary tree is. It's a tree where every node can have 0, 1, or 2 children. Okay? Okay? Great. We're going to use what we just did with that summation sign. We're going to use it. This is level 0. Level 1, level 2, level 3, etc., etc. Okay, question. This is level 3. How many nodes are there on level 3? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I want to point out 3 different things. How about level 4? Well, there's only 1, 2, 3, 4 on level 4. But how many can there be? And the answer is as follows. Look, there can be only 1 at level 0. because that's the root. There can be 2 here. There could be 4 here. There could be 8 here. Okay? At level n, there can be at most 2 to the n nodes. At most. It means if everybody has 2 children, then at level n there'll be 2 to the n children. Okay? Great. Let's do the next point. Okay? Great. Now, I want to add up a tree. I have a tree of length d for depth, the depth of the tree. How many nodes can I have? Okay? 2. Let's say it nicely. There are at most, again that's English, at most means this is the maximum amount that there could be. Summation L for level is equal to 0 to d. D is your depth of 2 to the L. This is how many nodes there can be in each one. Okay. Now, we just saw a formula for this. This becomes 2 to the d plus 1 minus 1 nodes in a binary tree of depth d. Three. Okay. Let me write this out and figure it out in a second. A binary tree. Okay, this is 3 rules about binary trees. And again, there's obviously a lot of rules about binary trees. I'm cherry picking those that exactly I know it will need. With n nodes has depth, okay, at least, okay, look, here I tell you the depth and we told you how many nodes you have. I want to go the other way around. If I tell you a binary tree has n nodes, question, what's the depth of the tree? Okay, so if I tell you a binary tree has n nodes, what's the depth of the tree? What's the maximum depth of the tree? Okay, and the answer is the maximum depth is you have a tree like this. A long snake. A long snake, you have n nodes. You're going to have, the depth is going to be n plus 1 or n minus 1, something like that. Okay, but I'm not asking that. I'm not asking what's the maximum depth of the tree. I'm asking what's the minimum depth. How much can you shrink it? Okay, and the answer is log of n. But we have to worry about the thing. Okay, log base n. Okay, because that undoes this. In other words, if I give you n is equal to this, I want to solve for d, you have to do logarithms of both sides. You get log of that. Okay? And it's at most n minus 1. Okay, so these binary trees we're going to use all the time, etc., etc. This is the math background. Now we start chapter 4. Chapter 4 starts talking about recursion and stuff like that. Okay, so, but you have to know the math background very well before we go further. Have a great day.